modeling. Dr. Rajendra Nagar has interests around computer vision, image processing, computer graphics, 3D shape analysis, and geometric processing. And he is a faculty in our electrical engineering department. With this introduction, I hand it over to Dr. Rangan Sen Gupta to welcome our guest for the day and take the event forward, please.
Thank you, Dr. Sankal. Good evening, everyone. I, Dr. Rangan Sen Gupta, on behalf of AID School, welcome all attendees to the Thar talk series, which is the webinar series of the school. I also take this opportunity to welcome Professor Mesbah, who is kind enough to be a part of this webinar. Professor Mesbah had done his BS in chemical engineering from University of Tehran in 2004, following which he has done his MS in chemical engineering and PhD in the area of systems and control from Delft University of Technology. Currently, he is an associate professor in the Department of Chemical and Biomolecular Engineering at UC Berkeley. Professor Mesbah's research interest lies in the area of intersection of optimal control theory, machine learning, applied mathematics to analyze and control of complex chemical and biomolecular systems. In particular, Professor Mesbah and his research group is interested in developing computational methods and control theory that enable learning, analysis, and predictive control of uncertain systems. Professor Ali presently has over 2,000 citations. Today, Professor will present on the topic performance-oriented model learning via constrained Bayesian optimization, a very relevant topic for modern days chemical engineering and chemical and allied industries, where we all talk of Industry 4.0. Thank you, Professor, for accepting our invitation and giving your time from your busy schedule to share your experience and knowledge with all of us through this webinar series organized by AID School at IIT Jodhpur. With this, I invite Professor Mesbah to deliver his eminent talk. Over to you, Professor.
Okay. Thank you very much. So I hope you can see my screen.
Yes.
Okay, good, great. Thank you very much for the introduction, for the kind introduction, and for the opportunity and for the invitation to basically give this talk. So today I'm going to talk about how AI, artificial intelligence, and machine learning methods can be leveraged toward learning predictive prediction models for basically optimization-based control applications. So let me get my pointer. Great. So let me set the stage first. So what is optimization-based control, or what is model predictive control, in other words? So let's say we want to go around this track. So how can we view and formulate this problem mathematically? Let's say our goal is to minimize, to get around the track, let's say in minimum time, right? So the objective is to minimize the lag time while respecting constraints that we are confronted with during this driving. For example, we would have to avoid cars, we have to stay on the road, we have limited acceleration, and so on. So a very intuitive approach to kind of view and formulate this problem is to really look forward and plan the path based on our knowledge of the road. In other words, what we can do, we can use a dynamic model to predict the future, right? And accordingly, we optimize our, let's say, acceleration, our speed, and so forth, in order to get around the track. So this intuitive viewpoint can be mathematically formulated as an optimization problem, meaning that we want to minimize the lab time, let's say, subject to a prediction model and some constraints that we would have to honor as we drive the car. But the challenge arises from the fact that all prediction models provide an approximation of reality. There are always phenomena and things that cannot be accounted for in the prediction models, right? So this necessitates basically replanning of our control actions, meaning that based on the feedback of the measurements and based on observing where we are, observing the road conditions, we want to resolve this optimization problem as we kind of drive the car. And through this, we can introduce feedback. So the whole notion of optimization control, optimization-based control or decision-making, or in other words, model predictive control, in short, MPC, is essentially to find the best control sequence over some future horizon of n steps through solving such an optimization problem online. So in this optimization problem, essentially we're trying to optimize some objective function. This could be simple set point tracking objective function. It could be some economic nonlinear cost function that is subject to a process model, a prediction model, setting constraints on the states and the inputs of your system. And basically the way that we go about this, we use this prediction model to essentially, let's say in this case, in the simple case of set point tracking, to minimize the difference between the set points and the current state, right? And this in order to design our input sequence. But in order to confer feedback to this approach, we kind of do this in a receding horizon manner, meaning that at every sampling time t that we measure, we observe the system or the process, we kind of reinitialize the model. In other words, we pass our measurements to the optimizer to reinitialize the model in order to repeat this replanning. So this is known as receding horizon control, or MPC, and it has been extensively used in a wide variety of industries and applications. So first, from its inception back in the 70s in the chemical industry, so you can see that now MPC is being applied to a wide variety of applications and systems. And what is really interesting to note here is the diverse time scales and, in fact, length scales of the systems and processes that MPC is currently being applied to. So we have production and scheduling problems, which are kind of performed on day to week time scales, all the way to automotive applications, embedded systems that in which we're talking about really millisecond, microsecond, even nanosecond time scales. And these are the time frequency that we will have to kind of solve this MPC or this optimization problem online. So basically the key ingredient of MPC are a prediction model, online optimization, and some tuning, some calibration that we would always have to do, like any other control scheme, in order to choose parameters, the weights in the controller. And really the question is how machine learning can be leveraged toward addressing these three issues: learning prediction models, enabling faster online computation of the optimization problem, and how we can basically systematically select the parameters, the calibration parameters of MPC. And the point is machine learning and AI can really be leveraged. There are great opportunities really for establishing models from data-driven models from input-output data. In fact, also combine data-driven models with high-fidelity physics-based model. Also, they can be leveraged toward speeding up computations, and as I mentioned, also systematic selection of the tuning parameters or of MPC. So in this talk, I'm going to primarily focus on the topic of learning prediction models. So we're gonna basically talk about two different approaches. In the first approach, the question that we're asking is how machine learning can be leveraged for online calibration of prediction models using real-time data. And this is a particularly important problem, especially in the context of safety-critical applications. And the point is, as the name implies, MPC relies, model predictive control relies on a model. And many practical complex technical systems are hard to model, right? And they have time-varying dynamics that cannot be really modeled upfront using offline data. And the question is how we can learn these systems on the fly as we operate and as we control the system, how we can kind of learn the hard-to-model dynamics and accordingly adapt the models. And another key consideration to keep in mind here is handling uncertainties in this context is extremely crucial, again, for safety critical systems, for example, biomedical applications, energy systems, and so on. So as we control the system in this unknown, uncertain setting, we want to make sure that we respect the constraints of the system in a robust manner, meaning that we want to mitigate any undesired, unwanted constraint violations. And this constraint this constraint is very much like the example that I gave at the beginning of the talk. These are essentially some physical constraints in the context of chemical processes. For example, they would translate to pressures, temperature, concentrations that have to be, for example, respected. The other topic that we'll be discussing today is basically how we can really treat these prediction models, the underlying prediction models of these optimization-based controllers, as a parameter, as a calibration knob that can be adjusted over process runs, over process episodes, in order to enhance the quality of these models. So here, from passive learning methods in the first approach, we're more moving toward active learning approaches, where the idea is to focus on the performance-oriented quality of the models. So as opposed to learning models that have a good general predictive capability, we want to tune our models toward their intended applications. And in this talk, the focus would be on control-oriented performance of the models. So these are the two topics that I would like to share with you today. I'm going to begin with the first topic, and the question is how we can really calibrate our models, our prediction models, using real-time data. So to take a step back in MPC, essentially, as I mentioned, we are solving such an optimization problem in an online manner, and we are applying the optimal inputs to the process, right? And the thing is, the processes that we deal with in real life situations, they're always subject to disturbances and uncertainties, right? There are exogenous disturbances, there are unaccounted or unmeasured disturbances that have not been taken into account in this model. And on top of that, all models are some approximation of the reality. There's no complete model, right? So especially again in more emerging applications, we are dealing with sort of dynamical behavior that may not be easily modeled, or the dynamics of your system may change over time. Therefore, there is always some degree of time model mismatch between the model that has been used in the controller and the true behavior, the true dynamics of your process. And this mismatch can really degrade your model predictions within the MPC, and accordingly really lead to fragile solutions of your controller. And the whole point in online model calibration is to mitigate this plan model mismatch. So let's take a step back and very quickly go over how, take a look at the traditional approaches to process modeling in MPC. So the traditional approach is to use offline data to develop some model. And then this model, essentially in a separate set, can be used to design your controller. Essentially, the modeling and the controller design are treated separately. Basically the procedure is sequential, and the model is learned based on or developed based on offline data. And there are a wide variety of modeling approaches here that have been extensively applied very successfully, I would say, over the years. So obviously, whenever we can accommodate physics into our models, it does make sense to take physics-based modeling approaches, right? Especially when we have this specialized knowledge. Again, for emerging applications for complex systems, really the physics may not be fully known, right? And on the other hand, we have fully data-driven or system identification approaches that provide a more flexible modeling framework based on data, but obviously they suffer from the problem of basically lack of extrapolation ability. And as I mentioned, there are all these different modeling approaches to capture linear or nonlinear system behavior based on physics or fully data-driven and so on. But an important observation to make here is that most of these traditional approaches really do not provide a description of model uncertainty. And this is extremely, again, important in the context of safety-critical applications, safety-critical systems such as autonomous vehicles, biomedical applications, even certain energy and manufacturing systems, where it is extremely important to kind of to proactively account for these uncertainties that we have in the environment as well as in our models. So the fact that these approaches, these traditional modeling approaches, disregard uncertainty, force us to only rely on this receding horizon principle or on the feedback that we have in the controller to combat basically uncertainties and disturbances, right? So always feedback, measurement feedback has this power to partly mitigate uncertainties, but obviously in a very non-systematic way, and therefore your solutions and your control approaches can become fragile. So really, the remedy is to account for model uncertainty explicitly in the description of the system that we have. So again, traditionally how this is done is you lump all the disturbances, all the uncertainties that you may have in your system, right, in your knowledge of the system, actually I should say, in one term, and we call that the disturbance term W, right? And again, all uncertainties are just lumped in one term, and we can adopt either worst case or stochastic or probabilistic descriptions of these uncertainties. In other words, from data, somehow we would have to model this uncertainty W. And this would lead to essentially solving more sophisticated optimization problems. Now we are solving robust or probabilistic / stochastic optimization problems here. Once we kind of model the description of uncertainties using data. But again, the issue in this approach is if the description of uncertainty is kind of, again, learned offline, using your offline data, we lack this learning capability to deal with unmodeled dynamics and unmodeled uncertainties that could not be accounted for in the offline data, the upfront. So this leads us essentially to the whole notion of learning-based control, or in this context, learning-based predictive control. So here, the idea is actually pretty straightforward. The idea is to augment some nominal model of the process. So this is our nominal process model that can be established using traditional approaches that I mentioned. It could be either data-driven or a physics-based model, but we then augment this model with a term that is supposed to account for the structural time-model mismatch as well as the time-varying dynamics that may occur in the system, right? And really, then the primary question here is how we should represent this time-model mismatch term, right? This W term. So, as I mentioned, one approach is to take the worst-case view of uncertainties, meaning that we observe certain realizations of an uncertainty W. So these dots essentially are realizations of the uncertainty, and we can accordingly identify the worst cases for these uncertainties. So the maximum uncertainty realization and the minimum uncertainty realization, and accordingly we define some bounded deterministic or some worst case uncertainty description for W. And this uncertainty description is supposed to kind of model both the plan model mismatch and your noise. But one important observation to make here is that such an uncertainty description is state and input dependent, right? So it cannot really capture the dependence of your uncertainty model on the current state and on the current inputs of your system. And by the way, this worst case uncertainty descriptions are very commonly, in fact, used in robust optimization or robust MPC, and they can lead to quite conservative performance in decision making. Why? Because you are kind of performing your decision making based on worst case realizations of uncertainties, right? So an alternative view is to really use your data, these uncertainty realizations, again, these red dots, to establish or estimate a probability distribution of your of the uncertainties in some parametric way. So, for example, you can approximate the distribution of your uncertainties using a parametric normal distribution, a Gaussian distribution. This would give you a probabilistic uncertainty description that can be used to partly mitigate the inherent conservatism of robust decision making, in which you only use the worst case view of uncertainty. So this is again a typical assumption in probabilistic or stochastic decision making. But what we want to advocate actually in this talk is to take a completely different view of these uncertainties. So why not we leverage advances in machine learning and artificial intelligence to essentially learn some state and input dependent description of uncertainties, right? So we really treat these uncertainties W as a function of your states and inputs, right? So no longer these descriptions are state independent. Now, the fact that your uncertainty description can change with states and inputs essentially would allow you to account for unmodeled dynamics as well as basically time-varying dynamics, right? As you operate your system and as you gather more real-time data. And the point here is this state-dependent uncertainty description should be learned using some non-parametric approach, as I will allude to. So then, in this learning-based predictive control paradigm, so as I mentioned, we kind of augment this nominal model. This is the model that we have learned offline, either physics-based or data-driven, with this unknown function that is state and input dependent, but it is actually meant to represent time-varying dynamics and essentially the hard-to-model structural mismatch mismatches that have not been accounted for in the nominal model. The key question is how to learn this state-dependent uncertainty term or prime model mismatch term from data. And it turns out that GP or Gaussian processes basic Gaussian processes provide a very flexible and useful framework for learning state-dependent uncertainties in the context of learning-based control. So, as you probably know, GP is a non-parametric, non-linear regression approach, and the goal in Gaussian processes is to learn a function with error bars. So we are not only interested in learning we are not only interested in using data to learn some function, some state and input dependent function, but also we want to characterize our confidence in the function, meaning that we want to establish the uncertainty or the confidence bounds around the function. So really, GP, a Gaussian process is in fact is a prior over some functions, right? So meaning that we kind of represent our prior knowledge of a function here as a Gaussian process, and this Gaussian process is characterized in terms of some mean and some covariance. So typically the mean is assumed to be 0, but it could be any parameterized function, right? So here theta is our input and f is the output. So in Gaussian processes, we essentially aiming to represent a prior over functions using this Gaussian distribution, and this k, this covariance function, there are many choices for covariance function for representing the covariance function. One of the most commonly used one is the squared exponential function, and it is really meant to quantify the correlations among the inputs. So what is the key idea in GP? The key idea is your observations are basically jointly Gaussian with respect to the functions evaluated at the test points, right? So then if we utilize this result, this key idea, then the conditional formula will also be Gaussian, meaning that we can establish the posterior distribution, right? So we start with a prior that is Gaussian, right? Given that the observations are jointly Gaussian with respect to the functions evaluated, with respect to our function evaluated at the test point. So this is what you see here. So then you can establish the posterior distribution, which would also take the form of a normal distribution, a Gaussian distribution that is defined in terms of the mean and in terms of the covariance matrices. So essentially, your posterior function, when evaluated at the test points, you can see that this posterior function can be viewed as some interpolation scheme among these observed data points, right? So and not only you interpolate among the observed data points, but you also essentially characterize the uncertainty or this confidence bound. So at the observed data points, obviously you have zero uncertainty because your system has been observed, right? Whereas other places, you not only estimate basically the mean over the different priors, but also the confidence. And the nice thing here is we can analytically kind of establish the mean and the variance of our posterior distribution using the data, right? And since we're essentially representing the posterior with a Gaussian distribution, just knowing the first two statistical moments would be sufficient for characterizing the entire distribution of the posterior. So then what can be done here? We can use this notion of Gaussian processes to quantify, going back to our planned model mismatch model learning, we can use Gaussian processes to essentially learn the mismatch between what we observe. So this is our true observations of the system minus the predictions of the nominal model. So essentially this represents your planned model mismatch, right? The G function that we would have to learn. And this can be learned using Gaussian processes by collecting data. So essentially input-output data. Here's for notational convenience. I'm just augmenting my states and inputs and denoting inputs and states by Z. So if you form your data set as the difference between actual measurements and the predictions of your nominal system, that would be your output. So this is the mismatch term, and your inputs would be XU, essentially the pairs of states and inputs. So you can use this data set over some history of your process in order to compute the mean and the covariance of your planned mode mismatch model. So essentially, we are representing the planned mode mismatch term by a Gaussian distribution, and we can evaluate the mean and the covariance of this Gaussian distribution in real time as we gather more data. This leads to the following formulation of MPC. So we kind of formed a version of this MPC problem before, but now what we are doing, we are essentially augmenting this nominal system with this model, this GP representation or GP approximation of the unknown planned model mismatch term. And this is fully described by the mean and by the covariance that we learn from data in real time. Obviously, this problem in its in the form that is presented here is intractable because we would have to propagate the uncertainty. So as I mentioned, dealing with uncertainties is also crucial when we're talking about models and model learning in this context. Why? Because we want to make sure that our solutions are not fragile with respect to these uncertainties. And for this reason, we define our objective function not deterministically, but in terms of the expectation of the objective function to essentially account for the uncertainties and the uncertainty description that have been learned through this GP. So then the next question is how we should propagate these uncertainties, and there are various ways. So one very useful approach in our view is the stochastic programming approach, which would lead to really a scenario tree-based interpretation of decision-making or optimization under uncertainty. So here the idea is to use this model of uncertainty that we have learned from data and is being adapted in real time to kind of draw samples or draw scenarios of uncertainties, right? So we are using this normal or this Gaussian distribution to draw samples for the uncertainties, and accordingly we can construct a scenario tree. So starting from our initial state that has already been observed, so this is known. So depending on how many scenarios we consider for uncertainty, so in this scheme I'm only considering 2 scenarios. So then we can go. Then essentially your node, your parent node, branches off. Again, at this point, if we consider 2 scenarios for uncertainties, again it branches and so on and so forth. So essentially, you are representing your uncertainty propagation using this scenario tree. And one thing to keep in mind here is the size of this tree grows exponentially. Why? Because at every node, so you essentially branch depending on how many scenarios or how many realizations you want to consider for these uncertainties. And keep in mind that these uncertainties are state and input dependent, right? Meaning that essentially your tree is not fixed, as opposed to a worst case scenario tree that is fixed. Here your tree is kind of being adapted as a function of inputs and output, as a function of states and inputs. And again, a common practice in stochastic programming is that you stop branching you start branching your tree after some robust horizon, after some number of steps into the future. Why? This is because to mitigate the computational complexity of these uncertainty propagations. So by avoiding branching after the robust horizon MR, so essentially you no longer consider multiple scenarios for your uncertainty. Okay, so but there's an important computational question to be addressed here. If the goal is to use this framework for online optimization, online decision making, and that is how to generate these scenarios or these, if you like, samples of uncertainties offline, because reconstructing the scenario tree in an online manner can be pretty expensive, especially when you're talking about real-time control applications for, again, advanced and modern complex systems in which we may have to operate the system at really micro second timescales. So here, what we can do, so really the goal is, the idea is to avoid online generation of the scenarios. And what we can do, we can very conveniently, in fact, leverage the fact that the conditional probability distribution of uncertainties is also Gaussian, right? So given that these uncertainties, the conditional probability of these scenarios condition on given inputs and states is Gaussian, right? So we can very easily generate these scenarios offline, right, from some normal distribution, and then use the mean and the covariance of this uncertainty description that we're adapting in real time based on the real-time data to transform, to move these scenarios, right? So this would allow us to really deploy such a learning-based decision-making scheme in real time, and to kind of significantly mitigate its computational complexity, because all the scenario generation is done offline, and at each point you simply just move and adapt your scenario. So this would lead to this would in fact lead to some adaptive scenario tree. So your scenario is no longer fixed, it's no longer rigid, such as the case in which the scenario tree is built based on worst case uncertainty description. Here, since your scenarios are state and input dependent, essentially you're going to get an adaptive scenario tree. And as I will also demonstrate on a real application, such an adaptive scenario tree, learning-based scenario tree, would allow you to significantly mitigate the inherent conservativeness of robust decision making. So again, I don't want to get into the details here, but really the point here is the location of these scenarios move as a function of the predicted states and inputs, and then that can really improve your robust control performance by mitigating the conservativeness of robust decision making. Okay, so let's see how this works in practice. So in my lab, we are heavily engaged in designing developing prediction models and designing advanced controllers for low pressure plasmas for plasma medicine, for biomedical applications, essentially. So what you see here, this is an atmospheric pressure plasma jet that we have in the lab. Essentially what you have a dielectric tube, you pass some inert gas such as helium or argon, you apply electric field, and what you get as a result of it is this very highly reactive medium, right? Where you get reactive species, you get thermal effects, you get electric field, and it has been postulated and in fact shown that this reactive medium can have a variety of medicinal and therapeutic effects. So these plasma jets actually in Europe, they're currently being used for cancer tumor reduction and many other medical applications that I won't get into right now. So this is basically how a commercial device looks in practice. So in this application, it's being used for wound healing applications. And again, keep in mind that this is medical application. meaning that this is a safety critical application, obviously guaranteeing and ensuring the safety of the patient is of utmost importance in such an application. It is also challenging in the sense that look at the sampling times. Here, the sampling times we're looking at 10 to tens of millisecond sampling time, meaning that your control algorithms or should be really fast and efficient computationally to be able to deploy them in real time. And also, I'm not going to get into the physics here, but this is an extremely complex process in terms of the physics of plasmas, as well as the complex interactions of the plasma with let's say with a biological tissue. These are really unmodeled. They're unmodeled behavior, and there's no mechanistic knowledge basically to be able to model the interactions of plasma with, for example, with the cancer tumor. So what we did here, we first used very well-established system identification methods, in this case, subspace identification, to identify a fully data-driven model of this plasma jet, right? So again, this is a very simple model, fully data-driven, that essentially accounts for the inputs, the two inputs that we have, the power applied to the jet and the gas flow rate, and it models basically the temperature of the surface and the cumulative thermal effects that are being delivered to the surface. So here we are aiming to control the thermal effects that are delivered to a surface. And what we did essentially, so this is our nominal model, and we, in addition to this, we used a Gaussian process model, really what I explained, trained using 100 data points to account for the complex and unmodeled dynamics of this plasma jet. And without going much into the details, these are the key results that I want to discuss with you. So here, the idea is to deliver some desired amount of thermal dose, that is denoted by CEM, as quickly as possible to the surface. So 10 minutes is the desired amount of thermal dose that we want to deliver. And obviously, this is a safety critical application, meaning that no time we are allowed to kind of violate the surface temperature for patient comfort and safety. So this is an upper bound and an upper constraint on the surface temperature. And what you see here is this is the performance of, so here I'm comparing the performance of the learning-based scenario adaptive MPC with the worst case MPC that relies on the worst case description of uncertainties with a rigid scenario tree. So these are both scenario tree optimizations, as I kind of explained, but in one case, the scenario tree is adaptive based on the GP that is being learned and adapted online. And in the other case, in the blue case, essentially the blue profiles, the scenario is based on the worst case description, so it's rigid. And really, this is what I meant by conservative performance of robust decision making. You can see that in the worst case algorithm, essentially, we would be able to deliver the desired amount of dose. But this is done in a very conservative manner, and it will take a much longer treatment time to deliver the desired amount of thermal dose to the surface. But with the learning-based MPC, using the GP and scenario tree adaptation, although we have significant thermal mismatch, really our initial model here, this is a very simple model. This is a very basic model given the complex dynamics that we have here. But the GP thermal mismatch model is able, in fact, to significantly reduce this thermal mismatch, and as a result of that, you can see a much faster delivery of the thermal dose. And basically, this is because with this adaptive tree, you no longer have a very conservative performance. You can really push your temperature to the limits, to the constraints. Whereas in the worst case algorithm, the temperatures are far from the constraints, and therefore the dose delivery happens over a much longer time horizon. And this is extremely important, again, in the context of plasma medicine, because really we're talking about treatment times of 2 to 3 minutes, right? So the faster we can deliver a dose, the required amount of dose in a safe manner, obviously, the better it is. Okay, so what I kind of presented so far, let me see how we're doing on time. So what I presented so far, I basically use the available online or real-time data to adapt the model. So this can be regarded as active learning in the sense that I did not excite the system in order to generate informative data for model learning. I just used the existing, the available closed-loop data that I was gathering from the system. So what are the key advantages of passive learning approaches? First of all, as you saw, we could readily incorporate them into decision making, right? So formulation-wise, they're easier to work with, and more importantly, they would enable robust constraint handling. Again, constraints are extremely important for safe learning. But on the other hand, here we are making a big assumption, and the assumption is this available data is sufficiently informative, right? And this may not always be the case. So really, this closed-loop data, this real-time data, in the absence of any active learning mechanism, may not be informative to learn the best models. So then the alternative that we would like to move to is to basically actively collect data during the operation. So what we want to do, we want to effectively explore the system or the process dynamics by approximating the information gain of future data. And accordingly, we want to balance the exploration and exploitation effects of our inputs to the system. So essentially, the goal is to produce more informative data for model learning actively by balancing this exploration exploitation. However, the challenges are handling constraints and establishing the theoretical guarantees of your decision making or optimization algorithm or control algorithm might be more challenging. And also, generally speaking, they are less computation efficient. So quickly, in the next 10 minutes or so, the second part of my talk, really what I want to do, I want to demonstrate how prediction models, again, in the context of MPC and optimization-based decision-making, can really be treated as a calibration now, as a parameter that can then be adjusted over different process rounds or episodes in order to kind of enhance the performance-oriented quality using this active learning mechanisms, meaning that through balancing this exploration effect. Again, the key notion is to really treat the prediction model as a parameter. So what we do here, we really try to solve some optimization problem, right? So we want to minimize some function, and this function, it provides some closed-loop measure, performance measure, subject to the constraints, and our decision variables theta. They essentially could be any parameter, any tuning parameter, any tuning knob that you have in your controller. But in this talk, I'm going to really limit my discussion to the model parameters. Let's say you have some physics-based model or some data-driven model. So the parameters of this model would constitute your decision variables here. And these functions, this cost objective function f of theta and the constraint c of theta, these are essentially some closed-loop performance measures of interest. And let me be clear with the term closed-loop. So let's say you have some model-based controller. It could be MPC or any other controller, right? So when you apply this controller to the real process, or in fact, if you have high fidelity simulations. Again, this is very commonly done in practice, right? In practice, if you have high fidelity simulations, you may not be able to use them for controls. Why? Because high fidelity simulations are expensive. Alternatively, what you can do, you can learn control-oriented models from high fidelity simulation and high fidelity models in a data-driven manner and use these reduced order control-oriented models for designing controllers and optimization and whatnot, right? So the idea here is either with the real process or with some high fidelity simulations, you kind of generate closed loop data. And keep in mind that, again, your high fidelity simulations are subject to uncertainties, and for that matter, your experiments are also subject to disturbances and unknown uncertainties, right? So essentially, what you want to do, you want to utilize this closed loop data, either simulations or real data, in order to basically compute some performance measures of interest, either cost functions or and constraints, right? So here I'm formulating this probabilistically. Why? Because we have uncertainties. So and these uncertainties are denoted by delta. And obviously, the first question is how to really measure these objectives and constraints. Keep in mind that these objectives and constraints are kind of black box in the sense that you may not have closed form expressions for your closed loop costs or closed loop constraints. So what you can do, you can take sample average approximation of these performance measures, meaning that you can take, let's say, m samples of your uncertainties. So these are m realizations of your uncertainties. In other words, m realizations of these uncertainties, and essentially you approximate your costs and constraints in a sample-based fashion. But keep in mind that on one hand, these sample-based approximations are unbiased, so this is a great property. So thumbs up there. On the other hand, these approximations are noisy, right? Because basically the variance that you get for these approximations can be large for a small number of samples. So then the question is, how can we really deal with noisy objective and unconstrained evaluations? Not only that, here, so not only your function evaluations are noisy, they are not necessarily differentiable either, and they are in fact expensive to evaluate. Again, keep in mind that we are either running the real system, this is episode-to-episode learning, or run-to-run learning. So if you are running high fidelity simulations, those are expensive. If you have running experiments, again, you may have limited budget for running your experiments. So these are the three key features to keep in mind in solving such a black box optimization problem. Again, functions are noisy, not necessarily differentiable, and expensive to evaluate. So therefore, the optimization strategy that we want to use to solve this problem should be derivative-free, right? Why? Because again, your performance measures are black box, so we don't have the gradients. Ideally, we want to search for the global optimum. Since these function evaluations are expensive, we want to make as few calls for computing these functions as possible. And last but not least, the optimization algorithm should be able to account for the errors in these functions. So you should be able to handle noisy measurements. So for this reason, again, given that this function may not be differentiable, so we would have to resort to derivative-free optimization. And I'm not going to go over this slide. There are obviously a wide range of derivative-free optimization methods. So on one hand, we have Lipschitz-based partitioning techniques. Take grid search methods. So what is the challenge with grid search methods is that they rely on many function evaluations, right? On the other hand, we have stochastic derivative-free optimization methods, such as random search. Again, they are better in terms of their computational complexity relative to grid search, but still they may require a good number of function evaluations. And obviously, we also have deterministic surrogate-based search algorithms, one of which Bayesian optimization, or BO in short, which really strives to learn a surrogate model for the objective function and constraints, and then using this surrogate model in combination with some acquisition function, we want to actively learn basically the decision variable. So let me give you a very high-level overview of how Bayesian optimization works. So essentially here, we're talking about a family of algorithms that are specifically suited for solving black box optimization problems in the presence of noisy functions and noisy observations. So the basic idea, as I mentioned, is to first establish a surrogate model using data. So we first learn a surrogate model of our objective function using this initial set of data. And then we combine this surrogate model with some acquisition function. And this acquisition function really informs how we generate data. So here, this acquisition function, denoted by alpha, essentially should provide some measure of expected improvement as we kind of march forward. And there are many choices for surrogate models that can be used to learn these objective functions or constraints. So here, since we've already covered Gaussian processes, I'm going to stick with Gaussian processes. And the basic idea of BO is as follows. So here you see the objective function. Again, this is the surrogate, a GP representation of the objective function, the surrogate model that we have learned. What you can see, obviously, we have the mean and we have the confidence intervals. So then this acquisition function essentially helps us specify the next point that would essentially maximize through maximizing some acquisition function. And this acquisition function, the important thing is to note here is that balances sampling around the current minimum and reducing the uncertainty in other regions of space. So if you sample in a region that has a large uncertainty, essentially you're exploring space, right? So you're trading off essentially on quality, the performance quality, and uncertainty reduction exploration. So your performance will be better if you stay closer to the mean, but if you explore regions with high uncertainty, essentially you're learning the dynamics. So your acquisition function assists you in doing so. There are many choices of acquisition functions, improvement-based policies, optimistic information-based policies as well. So here, one very useful choice for the acquisition function is the so-called expected improvement acquisition function. Why? Because they can be solved essentially analytically, as I will demonstrate here. So your expected improvement acquisition function is essentially trades off the quality of your estimate, that is the difference between your current best or incumbent solution, denoted by eta, and the mean of your and the uncertainty. So this mu and sigma, these are established from your surrogate model, right? And really what you want to do, you want to maximize this this acquisition function, And given that your surrogate model is Gaussian distribution, these are essentially, this acquisition function is fully determined analytically, because these are essentially the cumulative distribution of a Gaussian distribution and a Gaussian distribution, indeed the probability distribution of a Gaussian distribution. So the key question is, this acquisition function doesn't really account for the constraints. That's how to account for constraints. And the second question is how to define this incumbent solution, right? So here what you see is Zn is the scaled incumbent solution. And the question is, what is the incumbent? What shall we consider as the best available solution or incumbent solution? So in fact, constraints can also be dealt with in the same manner. So what we do, we again can learn some GP surrogate model for the constraints, and then we add a weight to our acquisition function. Essentially, this weighted acquisition function, which again can be solved analytically, tells us the expected improvement when the constraints are fulfilled. And The other important question is what we consider, what we take as the incumbent solution. And this incumbent solution can be essentially approximated by the best mean value that satisfies the constraint. So you have essentially two options. You can either take the best value of the function or the best mean value. And best mean value is less sensitive, is regarded to be less sensitive to noise, especially in stochastic settings. So there are many important details, but just to give you a bird's eye view of the algorithm, essentially what you do for some budget that you have allocated for experimentation, either using a high fidelity model or real experiments, you fit some surrogate models, some Bayesian surrogate models. So GP is a commonly used one to the observations of your essentially objective function, and then you find decisions that maximize the acquisition function, and then you repeat this, you sample, so you apply, you sample, and then using the new data, you update your surrogate model, and basically until your budget is exhausted. And you may wonder, what is the point of replacing this black box data-driven optimization with the sequence of many optimizations? So essentially, because we're replacing one optimization, this was our original black box optimization, with a sequence of maximization problems that essentially maximize the acquisition function. But there are two good reasons for this. First of all, the objective function was expensive, and also derivative information was not available, whereas the acquisition function is basically derivative is very fast to evaluate, very quick to evaluate, and also we have analytical expression for it, and therefore the derivative information is available. So very quickly to demonstrate the utility of such an approach for performance-oriented model learning. So this is an application for a bioreactor, a relatively complex bioreactor. So what we did here, we really develop a hybrid model, meaning that we had a high fidelity model of the bioreactor. And the question that we posed was how we can adapt and learn this hybrid model in a performance-oriented way over bioreactor runs. So to this end, we used the high fidelity model to first train some residual neural network, right? So we essentially trained a neural network based on the high fidelity data generated offline. And then building on the notion of transfer learning, we kind of adjusted the parameters of the last layer of this neural network based on run-to-run process data, right? And the idea here was how we can use this Bayesian optimization, in fact, constrained Bayesian optimization, to kind of adapt the parameters, and in other words, the quality of this model in a performance-oriented way. And this is basically the key result that I would like to discuss with you. So what you can see here, this yellow line, this is our theoretical best performance, right? By solving an optimal control problem under the assumption that you know everything, and there's no uncertainty in the system. What you see here as the red profile, this is closed loop identification. So what we are doing, these iterations correspond to the different batch runs or process episodes, if you like. So in closed loop identification, what is traditionally done is you collect data, closed loop data. After the run, you re-adapt your model, and you re-adapt the model, and so on, right? Whereas what you see in this performance-oriented model learning using Bayesian optimization is kind of depicted by this blue profile. And you can clearly see that given a fixed budget, right? Again, this is important. We have a fixed budget. Given a fixed budget, you can really push the performance toward the theoretical best performance through really learning the model in a performance-oriented way. So here we are adapting this last layer of our hybrid model, of our neural network model, in a performance-oriented manner in order to really maximize the product quality and the end of the process. So with this, I would like to conclude the talk. So we kind of talked about two different paradigms, two different viewpoints for model learning in the context of decision-making, optimal decision-making. In the interest of time, I just want to leave you with the message that we are living in a very exciting time. There are really exciting opportunities, both for research and new practices. It's really up on us to explore these opportunities. So with this, I would like to thank you for your attention.
Thank you, Professor Mesbah. It's a nice talk and a very exciting talk. So the floor is now open for questions. Anyone with a question can write on the chat box. Professor Shantanu Chaudhary, if he wants, he can ask the questions.
Thank you for this exciting talk. I think it is really opens up various possibilities of use of machine learning in decision science, and particularly in the controls domain. And I really, this in terms of, I have just one very general question. That is, see, these are all machine learning applications. In a controls domain also has a possibility of a failure, in the sense that machine learning is always with a certain kind of accuracy by which we can model. And how do you handle, what is your proposal in terms of handling scenarios where there is an error? See, I can only have 98% or 99%, there will be always 1% error. So how do we handle such scenarios?
That's a very great point and very great question. So let me just go to this slide. So indeed, these models, at the end of the day, these are data-driven models, and the performance can be limited depending on the quality of the data and the approximations and so on and so forth, right? And in the context of control, again, especially for safety critical systems, it is extremely important to kind of proactively handle these uncertainties, right? The uncertainties that we get with our model predictions, in this case, machine learning based or data-driven based. And here, the paradigm of model predictive control or optimization-based control in general would allow us to kind of handle these uncertainties through constraints. So the point that I did not really elaborate too much in the interest of time was we want to achieve safe learning-based control. And by safe or safety here, we mean we want to provide guarantees that our constraints, which are physical constraints of the system. Again, very simple example, you have a chemical reactor, right? Your pressures and temperatures should remain below some limits, otherwise the reactor may explode, right? So you want to make sure that these constraints are fulfilled at all times in the presence of uncertainty. So then the point is, you not only want to learn prediction models, but also you want to quantify the uncertainty associated with these prediction models. And then the second point is that you want to leverage these uncertainty descriptions that you have learned using real-time data toward guaranteeing the constraint satisfaction. And in this way, you can kind of enable safe learning, right? Which is, again, in the context of safety critical systems and real applications would be crucial. And there's a lot of control theory research in this area, really on the issue of how to ensure constraint satisfaction, how to guarantee constraint satisfaction.
Yeah, that's a very practical problem for any kind of deployment of these kind of algorithms and systems. Thanks for your answer, and thanks for your very nice talk, and very illuminating talk, in fact, touching upon various aspects.
Any other questions?
Professor, can I ask question, Professor Sengupta?
Yeah, please.
Professor Ali, thank you for excellent talk. I am Deepak Fulwani. See, I have only one question. Your entire talk was about estimating this uncertainty, which is there in your model. And you know that for that we already have several ways by which we can actually estimate this uncertainty in the system. Like we have uncertainty in observers, like we can use this uncertainty observer to obtain this uncertainty in the model. And if I can't estimate everything, then there are ways by which we can ensure that remaining uncertainty which is there in your model by designing robust controller. So robust controller and uncertainty input observer, like unknown input observers, which we can use. The combination of these two can actually handle the class of problems what you discussed in your presentation. So I thought that can you like give some comparison, like what is the advantage of using this learning-based approach vis-a-vis the existing set of tools what we already have in terms of uncertainty input observers and robust controller, which can be combined to handle these kind of problems?
Yes, thank you for your question. Again, great question. Indeed, so there has been several decades of research on robust control, as you know, right, as you mentioned. But the point is, in robust control, as is depicted here, really we use worst case descriptions of uncertainties, right? Again, we have a variety of robust MPC approaches. We either use a worst case description of uncertainties or a probabilistic description of uncertainties. And the issue here is neither of these approaches are learning based in the sense that they cannot handle state and input descriptions of uncertainty. So really the point is, as opposed to a rigid fixed description of uncertainties, we want to kind of transition to state and input dependent descriptions of uncertainty. Why state and input dependent? Because the states of your system can change over again, in the context of, again, complex sectional system. They can change over time. You can get time varying dynamics, right? And these time varying dynamics are hard to model dynamics. These may not be state independent. So if you have a case that, really worst case descriptions such as this one really bounds on bounded deterministic uncertainty description work, then robust MPC can be valuable, right? And it has been established and worked very well over the decades. But again, to your question, in this real application, so this scenario tree MPC is in fact a robust MPC, is in fact a robust control approach, which is based on a rigid description of uncertainties. Whereas this learning-based adopts this state and input dependent uncertainty description. And you can see how the performance is vastly improved. Again, why? Because a worst case, a rigid uncertainty description, either worst case or probabilistic, it cannot account for the variations of your system over time, or the structural primal mismatches. Whereas a learning-based with state-dependent uncertainty descriptions can. And really the hope is by moving towards learning-based, we kind of reduce the conservative performance that generally comes with robust control. In this case, this conservative performance leads to a faster treatment time of the patient using this plasma medicine device, right? I hope this answered your question.
Yeah. Thank you, Professor Ali. I just wanted to say that, like, we also have a robust controller. At the same time, we can also estimate uncertainty through unknown input observers. That gives you like a kind of convergence. Here, in case of learning, I can't say with guarantee that my algorithm will converge to the true value of uncertainty. While in case of deterministic approaches like unknown input observers, I can actually precisely say that my observer error will go to 0 as time goes to infinity, and then I can say that I am observing that unknown input. So if I use this combination of unknown input observer, means uncertainty I am observing through some deterministic approach and I'm using robust controller, then I can reduce that conservative controller which otherwise results because of overestimation of uncertainty or worst case estimation of uncertainty. So my question was related to like using this combination vis-a-vis this learning base where I can't actually give the guarantee that this entire algorithm will converge to the true value of that uncertainty which you have based on this input-output data. So of course it has its own merits because it can also be used like when there is no structure in the system or model-free kind of system. So of course it is also an interesting approach which can be tried along with the existing tools we have to handle such problems. Thank you, excellent talk, and I really enjoyed.
Thank you very much.
There is another question. I just read it for you, Professor Mesbah. Professor Tiwari asked that model-based learning is good to handle black box or gray box. Can you please comment on high-dimensional problems that can be handled?
High-dimensional problems. So the idea of MPC obviously has been applied to high-dimensional problems. So nowadays, with the advances in computing power and optimization algorithms, there are MPC applications with many really high-dimensional states, even on the order of 1,000 states. But as far as the learning is concerned, again, it depends on the methods. For example, in this GP Gaussian process regression model that I kind of introduced here, we do have this scalability challenge, right? Because this scales cubic with the number of data, right? Because of the fact that in order to compute the covariance matrix, you would have to invert the matrix and compute the determinant. So I would say it depends on the application and what method you use. Again, a potential computational challenge in terms of dimensionality with Bayesian optimization that I also talked about is the number of decision variables. You are limited in terms of the number of decision variables. Again, that can limit for large-scale addressing large-scale problems. That said, a lot of interesting research is going on in this field. So for example, again, going back to GPs, we have sparse GP representations, which alleviate this issue with scalability to a large extent. Or there are advances in Bayesian optimization that to essentially make Bayesian optimization more scalable. So it's a very vibrant and active field, and addressing high-dimensional problems is being really actively investigated. And there has been really interesting results recently.
Thank you. Any other questions? I have a question. Let me ask. So you are actually modeling the uncertainties with some stochastic model. So how you actually propagate this stochastic model with time?
Yes. So again, great question. There are various propagation methods. For example, my lab has extensively investigated polynomial chaos approaches, unstandard transform approaches, and so on. So here, really, what I presented in this talk, I am propagating the uncertainty, this stochastic uncertainty, using the scenario tree. So this is why I'm adopting this stochastic programming viewpoint, meaning that I'm drawing samples right from my distribution, and these samples represent various uncertainty scenarios, right? So there is approximation here because I'm approximating this distribution with a finite number of scenarios. But scenario-based or scenario tree uncertainty propagation has its own merits in terms of, first of all, for control, we can incorporate recourse feedback. And second, you can essentially deal with any type of probability distributions with any complexity, right? But there are other propagation approaches as well, such as linearization, unstandard transform, polynomial chaos, and so on. But again, here we did scenario-based kind of uncertainty propagation.
Thank you, Professor. So any other questions? Okay, since there's no other questions, thank you, Professor. Now I want to invite Dr. Toteja to give a memento to Professor Ali Mesbah for this beautiful talk.
Thank you very much. First, I think compliments to Professor Ali for very exhaustive but well-structured presentation. I'm sure many youngsters will be benefited by his presentation. On behalf of Jodhpur City Knowledge and Innovation Foundation and Indian Institute of Technology, I have privileged to present small token of appreciation. This is the craft stuff made by the local artisans, and I would request you to kindly accept it.
Thank you very
And,
much.
I also wish you come to Jodhpur, Rajasthan, and also see the lot of good things made by local artisans. And many of them you take away also with you. Thank you very much.
Yeah, thank you very much for this opportunity.
Thank you, Dr. Toteja. So I invite Dr. Manish to give a vote of thanks.
Yeah. So, Professor Mesbah, thanks again for the talk. And this memento will reach you in a few days' time. And we hope that you will like it.
Thank you very much.
Yeah, thank you. Let me also thank the audience for joining us for this talk. And looking ahead, the Thar talk series will continue. And the next talk will be in the area of DNA modeling and storage. And it will be delivered by Dr. Emily Leproust. And this talk will be delivered on 25th August. So basically 2 weeks from now. So we look forward to all of you joining for that talk. And thanks again for joining us. Thanks again. Good evening to all of you.
Thank you, Dr. Manish. Thank you, Professor Ali Mesbah, for this beautiful talk. We hope to see you in Jodhpur in the near future. Thank you.
Goodbye, everyone. Bye-bye.